So this talk will be on a model called One-Deterministic-Counter Automata. So we will shortly see what the model is. And this is a joint work with my guide, Dr. Sreejith, and Dr. Vincent Penelle from University of Bordeaux, and Dr. Prakash Saivasan from IMSC. So yeah, let me just jump to the talk. So this will be how the talk will be outlined. So initially, we will just see one counter automata for those who are not familiar with it. And then we will look at this model called One-Deterministic Counter Automata, or in short, ODCA. And then we will just say what are the results that we have in ODCA. And then we will look at this reachability problem of ODCA and look at the other results like equivalence and covering that we have for ODCA. So yeah, so what is a one-counter automata? So I think most of you know what one-counter automata is. But you can always see it as a finite state machine, or DFA, which have access to a counter. So what can this finite state machine do to the counter? It can increment the counter by 1, it can decrement the counter by 1, or it can choose not to do anything to the counter, right? And it can also do a zero test on the counter, like it can check whether the counter value is 0 or not, and then take transitions accordingly, right? So this is a one counter automata. Okay, I'm not going into detail. So these are the properties that we have for OCA. We know that for the equivalence of deterministic OCA is known to be in P, but for non-deterministic OCA it's undecidable, right? And the equivalence problem for weighted OCA is an open problem, even if the weights are from a field. Yeah. So what is this one-deterministic counter automata? Okay. So just like I said, the equivalence of non-deterministic OCA is undecidable. So we have a kind of a restriction on the, what if we have a kind of restriction on the counter, right? So this is one-deterministic counter automata. The semantic definition would be, it will be an OCA where all the runs will have lead of a particular word will lead to the same counter value, right? You can just maybe see it as a non-deterministic OCA. So a word will have like multiple runs, but any run you take, the counter value that you reach will be the same, right, for that particular word. So we have an equivalent syntactic definition as well. You can also see it as a finite state machine, which have access to a counter, and then you have a counter structure, right? So it's similar to an OCA, right? Except that now you have this block here, right? So this counter structure is also a finite state machine. So this makes sure that, so this is a deterministic machine. So it makes sure that the counter actions are always deterministic, right? So the finite state machine here, it can be a deterministic, non-deterministic, or a weighted machine. So here you can have deterministic, non-deterministic, or weighted transition. It can only test whether the counter value is 0 or not, right? But this counter structure here, it can update the counter. It can +1, -1, 0, and it can also do a zero test, right? So this ensures that the counter actions are always deterministic, no matter what happens in the finite state machine. So like I said, this ODCA, this finite state machine can be deterministic, non-deterministic, or weighted. If it is non-deterministic, we say it's a non-deterministic OCA. If it's deterministic, we'll call it a deterministic OCA. If this finite state machine is a weighted automaton, then we call it a weighted ODCA.
Sorry, so how is this different from the one counter automata?
So in non-deterministic one counter automata, let's say you have a run for a given word, right? So it can have multiple runs. Let's say you read AB, AB. So in one path, maybe you reach counter value 2. In the other, you may be reaching counter value 1, right? Now this basically leads to undecidability of this equivalence. But this ensures that, let's say you read AB, AB, any path you take, no matter what state you reach, the counter value is always going to be the same.
How is it repeating? So the finite state machine can still test the counter for 0?
Yeah, so it can have, so this finite state machine can have like two sets of transition. One when the counter value is 0, and the other when the counter value is 1. But it cannot update the counter. The counter updates are always made by a deterministic machine, right? Yeah, counter structure is deterministic machine.
Okay, and that is different from the earlier model.
Because now this ensures that any path you take, you reach exactly one counter value for a given word.
Right. No, I'm just saying the structure of. So in the your previous slide, you had the.
Yeah. So it only had this finite state machine and the counter. Right.
Right.
This is a deterministic. Yeah.
So the finite state machine is updating the counter and also checking
for the counter value whether it's like
now
0 or
that
not.
you've separated that update into another.
Yeah, so these updates are now controlled by a deterministic machine.
Okay.
But the transitions here can be non-deterministic. So now let's just look at a, yeah, yes. Uh-huh. Yeah, so both so they, like on a given word, both are taking transitions simultaneously. Yeah, sorry, I forgot to mention. Yeah, kind of, you can think of it. So basically, yeah, so reading, like this actions here in the finite state machine and counter structure are like happening simultaneously. Now, you can see that, okay, this particular model, this is actually, like this, you can see this visibly OCA is actually a subclass of this ODCAs. Like if you're in your visibly OCA, no matter what word you take, the counter value that you reach is always dependent on the input alphabet, right? So it's like it's a subclass of this deterministic, ODCA. Right. So you can just see with an example. So you can see this example language L1. It is A raised to n, B A raised to n. Right? So can a visibly OCA recognize this language? Is the first question. Can it? Because let's just assume that you increment, you always increment on a B, and no matter what you do on a B, you cannot recognize this using a visibly OCA, because you will have to count this number of A's here and the number of A's here, right? Let's say I chose to increment the counter. On an A raised to n, I can only increment the counter. I cannot decrement on the next A raised to n to check whether it's equal or not. So basically the input, it's like a visibly PDA, for instance. So the input alphabet will determine what operation that you do on the, what operation you are doing on the stack. So let's say, on an A, I can either always do a +1 or always do a -1 or choose not to do anything to the counter. Right. So here this language is recognized using a ODCA, but it cannot be recognized using a visibly OCA. Now the second one, let's say it's a function from.
So can you say?
So ODCA, you can have a one-state counter structure. So the transitions always, like let's say on an A, I do a +1. Yeah, no, you cannot have a one-state, yeah. So you can have a two-state counter structure. On an array A, I stay in that first state. On a B, I go to a second state. And now on the rest of the A's, I stay in the second state, right? And the finite state machine, yeah, you can always. So the second one, so this is a function. It's a function from AB star to say a set of natural numbers. So the function is given a word W. This f of W will return the decimal interpretation of the binary representation of W, provided the number of A's is greater than number of B's for any prefix of W, right? So clearly, okay. So let's say my word is ABA. Okay, I interpret A as 1 and B as 0. So the decimal binary interpretation is 101. So the output is, let's say, 5. Only if any prefix I take, the number of A's is greater than number of B's. So in this case, it will output a 5, right? Then if there is a prefix for which the number of A's is less than number of B's, I will not output anything. So this clearly cannot be recognized using a weighted automata, because you will have to keep track of this count of number of A's and number of B's. But this is recognized by a weighted ODCA. So yeah, so these are the results that we have in weighted ODCA. The equivalence of this deterministic ODCA is in P. So this is a straightforward thing, because this deterministic OCAs are actually equivalent to deterministic ODCAs. So the equivalence can be done in polynomial time. And
How is your model the same as a deterministic?
So when the finite state machine is a deterministic one, it is same as a deterministic OCA. Right? So when it's a non-deterministic one, it is, you can, there's an exponential blow up, but you can still convert into a deterministic OCA. But the tricky part is like when it is a weighted model, right? So we have got that even if the finite state machine is a weighted machine, we have got that the equivalence is actually in P, right? So yeah. So we know that the equivalence of weighted automata is in P. In some sense, we convert it into an equivalence problem of a weighted automata, which is not really straightforward. And then ultimately, you will get that for this weighted ODCA, you can do this equivalence problem in P. So yeah. Yeah, so again, we'll see what this one-deterministic counter automata is. So let's start with the, yeah. Yeah, you could say so. Yeah. Which one you're trying? Ah. Ah. Yeah, they are equivalent. No, deterministic ODCAs are not. So, yeah, you're right. Yeah, you're right. Deterministic ODCA. Yes, you're right. Yeah. Yeah. So before seeing what this, before yeah.
So can you go a bit slow on that slide?
Okay.
So we understand that deterministic one-counter automata are equivalent to one-deterministic counter automata.
Deterministic, one-deterministic counter automata. So.
Okay. I see. And then, so I mean, what is the advantage of this model? Can you?
So yeah. So let's say you look at non-deterministic ODCA, right? You know that the equivalence is not desirable.
Non-deterministic OCA.
OCA, yeah, sorry, non-deterministic OCA. So now, can you have a higher class of languages for which this language equivalence is desirable? So let's say you look at probabilistic push-down automata, right? You know that this is actually equivalent to some multiplicity equivalence of context-free grammar. You cannot do. So let's say even if the alphabet is a one-letter thing, it's actually yeah. Even if the alphabet is one letter, it's actually equivalent to this arithmetic entity testing, polynomial entity testing. So still you don't have a hope of getting a p-time algorithm. So now we are looking like, can we have a higher class in between this for which the equivalence is actually desirable and then maybe doable in polynomial time?
Higher class between what and what?
So if you look at like extension of OCA, weighted OCA, so it's one step towards solving the equivalence of probabilistic push-down automata. So for even if you look at probabilistic OCA, the equivalence is not likely to be desirable because of this non-deterministic action. But if you fix this determinism on the counter, you get a p-time algorithm for equivalence. So yeah, so before going into this one-deterministic counter automata, we'll just see some few simple examples of weighted automata. So most of you will be familiar with weighted automata. You can think of it as an NFI with weights, right? So for the scope of this talk, we'll assume that all the weights come from a field. So if you consider this following weighted automata, so can someone tell me what this weighted automata does? So on an A or B, I stay in P0. On an A, I can go to P1. And then on an A or B, I can stay in P1. So given a word, let's say AAB, what does it do? So it can non-deterministically choose this action A, right? Yeah, so it basically counts the number of A's in the given word. So now, again, let's say we take another example. So here you have a non-deterministic action on A, which goes to a state P1, and then on an A or B, we stay in that state P1 with weight 2, right? So all these weights are 1, but this weight is 2. So this again computes the decimal equivalent of the binary interpretation of that particular word. So let's say you can also see this as transition matrices. So you say you have an initial distribution lambda, which is 1, 0, right? So you are in state P0 with weight 1 and state P1 with weight 0, right? And now you have a transition matrix for delta n and delta p. So what this transition matrix say? This says that what is the weight of transition from state P0 to P0 on A? What is the weight of transition from P0 to P1 on an A? What is the weight of transition from P2 to P1 on an A? There is no transition, so you mark 0 here. And this basically marks what is the transition from P1 to P1 on an A, which is 2, right? So similarly, you will get a transition matrix for delta B. And your final distribution is 0, 1, because from P0, you don't have an output weight, but from P1, you have an output weight 1, right? So now, let's say you are given a word W is A1 to AN. How do you compute the output value for that particular word? So let's say you define this delta of W as product of all the transition matrices. You can get the accepting word of W as lambda into delta of W times eta. So this will give you the accepting word of a particular word. Now, in a similar way, we can also define ODCA. So you can, for simplicity, we'll just assume that it's a visibly system and you don't have any states in the counter structure, right? So there is a initial distribution on the finite state machine lambda. There's a final distribution on the finite state machine, which we call rho. And then for every letter A, there are two matrices. One is delta 0 of A, which will be taken when the counter value is 0. And the other one is delta plus of A, which will be taken when the counter value is positive. So now for any given word W, delta of W will be some delta R1 A1, delta R2 A2 up to delta Rn An, where R is Rn 0 or plus, right, depending on what the word is. Now, okay, so this is visibly ODCA, weighted visibly ODCA. So what we are interested in actually is in solving the equivalence of weighted visibly ODCA. Right? So this is a kind of difficult problem to tackle. And we have recognized that the specific reachability problem will actually, the core in proving this is to prove a reachability problem. With that reachability problem and the results there, we can actually extend the existing results on deterministic OCA to that of this weighted visibly OCA. So, so this is a reachability problem that we have. So it's a weighted automata. Yeah.
Abhishek, use the mic.
Yeah. So so the weight of the word is fine. I mean, it's just the product of the whatever the weights that you get on these individual transitions.
Mm-hmm.
But then after that, the accepting weight, I didn't get that last word, lambda, delta, W.
So you have an initial distribution, the state from which you start, and you have a final distribution, which basically here in this particular example, which basically marks the final state.
Distribution means distribution on the space.
On the
what is it?
states, yeah.
Okay.
So here you are weight 1 in P0 initially, right? And finally you are in weight P1 with output weight 1.
Mm-hmm.
So you are only interested in, like, let's say you read AAB, what is the weight with which you read this state P1?
Mm-hmm.
So so let's just say, for instance, I read AAB, right? So I can basically, it's this 1 0. So initially you have this 1 0, right?
Mm-hmm.
Then you multiply delta of A times delta of A times delta of B, right? Which will give you a matrix, right? But you need an output weight. So this output weight will, let's say I have an x1, x2, x3, x4. This basically will denote the weight with which I am in state, let's say, sorry, I mistake. This will give you a vector because you are multiplying it with the initial thing. So this will, let's say I have P1, P2. This is the weight with which I am in state P0. Okay, I should do something here. X0 and X1. So this is the weight with which I reach state P0 after reading the word. This is the weight with which I reach the state P1 after reading the word. But I am only interested in this X2, right? So I multiply it with the final distribution, let's say 0, 1, and then I will get this value, which is a required output weight.
Nice.
Yeah, so what exactly is this reachability problem that we are interested in? So this is our input. We have a weighted visibly OCA, A over a field, and you have an initial configuration. So like we saw, the configuration now will be a vector and a counter value, right, for a weighted ODCA. And we are given a vector space V, and we have a counter value M. So what is the question? Is there a run from this configuration V which can reach a configuration whose vector is in some complement of a vector space with some particular counter value? Right? So you have a configuration C. Does there exist a word which I can take from C and reach a configuration whose vector is in some complement of this given vector space V with a given counter value? So this is the co-BS reachability problem. Which states?
So what is the vector space here? It's the state space.
So yeah, so vector space, assume that the vector space is given as an input. So you have a basis for that vector space.
Okay, this is an independent problem.
It's an independent problem. Yeah. So we say that Z is a reachability witness if from this configuration C, you can read this Z and reach a configuration in this V bar close M, right? So this is a problem that we are actually interested in solving. And we have a result that this covious reachability is actually desirable in polynomial time, right? So this is proved by showing a pseudo-pumping lemma. Now, why is this difficult? So if you just look at a one-counter automata, you are always arguing about paths, right? So you only need to argue that you can cut short some path and still reach the required state. But when it comes to vectors, now you have to somehow cut out these vectors and still show that you are reaching the vector space that you want to, right? So it's not as straightforward as how you do in one-counter automata. So this covious reachability is actually proved by showing a pseudo-pumping lemma. So this is a pseudo-pumping lemma. Let's say you have a reachability witness, and let's say the maximum counter value that you encounter during the run of that witness is not bounded by some polynomial. Then you have a subword for that particular word Z, subword of that particular word Z, which you can take to reach this reach a configuration in this V bar close M. So given you have a large word, you can find a shorter word in short. Right? So this is a pseudo-pumping lemma, and how do you prove this pseudo-pumping lemma?
Prince, if I can interrupt. So just to, I mean, so what is the configuration here, and how are you getting a vector out of this particular run?
Vector out of what run?
So because you're saying that from a configuration you're running the automaton on this word, and then you're getting a pair, the first component of which is not in the vector space V.
So the vector space is given, assume that the vector space is given to you as an input.
That's right. But but the fact that you are eventually getting a vector whose membership you're checking in V, so what is the vector that is being generated when you run this word from this configuration?
When you run?
This, I mean, you have this word Z, say for example,
yes.
and you're running it on the configuration. So configuration probably would mean that you are
it's a
state.
Vector.
It's a
state and counter value. Like it's a vector and a counter value. So vector will basically denote the distribution that you are currently in. It's a distribution over the states. Right?
Oh, it's a distribution over the states.
So we are talking about weighted ODCA. So the configuration is a vector whose weights will denote the weight with which you are in each state, and you have a counter value.
Okay.
And then after reading this word, you are again getting a vector and a counter value.
That's right.
You are checking whether that vector is in this complement of a vector space.
Okay.
Yeah, so now what is the difficulty here? So let's just say I start from a vector x here, okay? I read that word, so this is how the counter value goes. The counter value goes up and comes back here. And let's say I am reaching this configuration y, configuration with the vector y, right? So the counter value is here, this is the word length. So I mark the point where I encounter the counter value n plus I here for the last time before. So this is the point where I see the maximum counter value in this run, which is this n plus m. Right? So I mark the point where I encountered this counter value n plus I for the last time before this maximum value, and I mark the point here where I see this counter value for the last time after the counter value, right? Similarly, I mark n plus j and these points as well. Right? So what I actually want to, let's say the word is of the form some ui, xi, vj, yi, wi. Is there a way to cut this some portion out? So when I cut out, what has to be taken care of? I have to ensure that I cut portions which have equal counter effect. Otherwise, my counter value ultimately might go below 0, right? So here I have to ensure that this portion and this portion have equal counter effect. Okay. So this is, again, in one counter automata, it would have been very simple. You can just look at the states and then cut this portion out. Right? But here, you'll need a bit of linear algebra to show that this is actually possible. Now, let's assume that I just plot these black points here, right? And the graph would look somewhat like this. So these are the points of last occurrences, and these are the points, so first occurrences, and these are the points of last occurrences. So let's say I start from 0, from x. I go to this maximum value, and I come down here, right? So there's a word from this x. So there's a word which I can take from here, which will reach here, right? So let's just say the transition matrix of that word is, let me call it M9. So x times M9 will actually take me to this point, right? So I have also two other matrices, A9 and B9. For the time being, they are identity matrices. So x9 times A9 times M9 times B9 is actually a vector in V bar, because this is the initial run that we have, right? So we assume that we have a long run which reaches V bar. We are trying to prove that we have a shorter run. So initially x times M9, x times M9 is already in V bar. Now similarly you construct other matrices. So now I take this matrix A8, which is basically the matrix corresponding to the word that takes me from counter value 0 to 1. And M8 is a matrix which takes me from counter value 1 to 1 here. And B8 is again the matrix which takes me from counter value 1 to 0. Again, you can see X times A8 times M8 times B8 is actually in V bar because it's the same multiplication taken in a different order. Right? Similarly, I have A7, M7, B7, A6, M6, B6, A5, M5, B5, A4, M4, B4, M3, and so on and so forth, right? And I have AS4, M0, B0. So for all this, X, AI, MI, BI is in V bar. Now, what happens next? Now, let's just say I am just enumerating all these matrices here. I have M0, M1, M2 up to MA, M9, right? And for the time being, I'll just assume this MI to be a 3 by 3 matrix for understanding it easily. So if I look at these matrices, I know that X, AI, MI, BI is in the complement of the vector space. So, yeah. So now I have a claim that, okay, now I can find a J such that Mj can be written as a linear combination of M0 to Mj minus 1, right? So why is this true? Let's say here it's a 3 by 3 matrix, and I have 10 matrices here, right? So I can see this matrix as a vector of size 9. So I can have only 9 linearly independent stuff. I have 10. So one has to be a linear combination of everything before it. So let's just assume that this M6 can be written as a linear combination of M0 to M5. Okay. So I can write this particular one as Xaj, and then substitute for this Mj. This is alpha 0 M0 dot dot dot. Bj is in V bar. Right? Now, from this we'll get that there is a J which is in the 0 to J minus 1, such that Xaj Mk Bj is in V bar. So why this should be true? Let's assume that this is not true. And for all of this Xaj Mk Bj is in V, then this is nothing but a linear combination of stuff which are already in V. And then it contradicts the fact that you are in V bar. So this cannot happen. So there is a K which is less than this, for which Xaj Mk Bj is in V bar. Right? So I assume like now you might have an idea like how this might be going. Yeah, thank you. So yeah, so let's assume this is it. So Xaj, there is some matrices here, Mk, and then something here, and then Bj. You know that you already know that Xaj Mj Bj is in V bar. Now here you have got that Xaj Mk Bj is in V bar. So it basically says that this portion multiplied by this portion multiplied by this portion is actually a vector in V bar. So you can safely remove this portion, remove this huge matrix Mj, and replace it with this matrix Mk. Right? This ensures that equal counter value, like you have the counter effect that you removed is actually equal on both sides. So you'll get a shorter run, but the maximum counter value encountered is smaller. So this is a pseudo-pumping lemma. So this is pumping down. Similarly, you can have a pumping up, right? So let's say you have a word which starts from here. Let's see it goes counter value up here and so on and so forth. It reaches D, right? You can apply this cutting multiple times here and bound the maximum counter value encountered. So here you can apply this cut. Here you can apply this cut. Here you can apply this cut, right? So in any run, you can bound the maximum counter value encountered during the run for this reachability problem. Right? So now, if you have bounded the maximum counter value for the ODCA, you can always construct a weighted automaton equivalent up to that counter value, and then check for reachability. So with this pseudo-pumping lemma, you already have that your reachability is desirable in P, right? Now for equivalence, you'll need an extra property, which is this special word lemma. Right? So the special word lemma, so this is something similar to that what Valiant had for one-counter automata. So let's say you have a reachability witness, then that reachability witness has some sort of special form, right? So with this special form and the pumping lemma or pseudo-pumping lemma, you can actually extend the techniques from OCA and then prove the equivalence of OCA. It's not a straightforward proof, but with some effort, like you can try and there are like similar techniques inside the proof that you have to do something like this, and then by applying this, you can somehow get the equivalence of ODCA, but we are not going into that. So this special word lemma is actually was a surprising result for even us. So let's say you look at the lexicographically minimal reachability witness. So let's say Z is the minimal reachability witness from some C to some V bar cross M. Then this Z has a special form. The word is of the form U y1 raised to R1 W1, y2 raised to R2 W2, And the length of this u y1 w1 y2 w2 is actually polynomially bounded. And R1 and R2 are also polynomially bounded in the input size. So yeah. So it actually, so you have to note the fact that it's a lexicographically minimal word, right? It's not just any minimal word. So lexicographically minimal in the sense the word has to be of the smallest size, and then it should come first in the lexicographical order. Now, how do we prove this? It's again similar to what we saw before, but there's a bit of combinatorics on word to be applied here to get this result. So let's say you start from counter value n, and you reach counter value m, right? So similar to like what we did before, if you choose a sufficiently large d, you mark this point n minus I, and n minus the first occurrence of the counter value n minus I, and the last occurrence of counter value n minus I minus d, right? You do that for all these values in between. So we show that if this, the minimal, if this d is chosen large enough, there is a very big factor which repeats in this word, right? So we say that, okay, let's say we come from here to here. The factors might be overlapping, but you have a very very big factor which repeats in this word. So this is what we are interested in proving first. So let's just assume that I plot this, just those points like this as a straight line. So again, I am marking the matrix M0 as the one which takes me from, in this example, counter value, let's say 50 to counter value 9, right? And this is my B0, which takes me from counter value 9 to 0. And I have a matrix A1 which takes me from counter value 50 to 49, and then M1 which takes me from, let's say, counter value 49 to counter value 8, and B1 which takes me from counter value 8 to counter value 0, right? Similarly, I can have M2 which takes me from counter value 47 to counter value some 7, and B2 which takes me from 7 to 0. So likewise, I define this M2, A2, M2, B2. Again, I can see that for all of this, X, AI, MI, BI is in V bar, right? So I just list these matrices, M6, M7, M8, M9. So again, I list the, so there's a, that's enough. So yeah, so again, for the sake of simplicity, I'll assume that they are all 3 by 3 matrices. And I arrange this X0 to X9 in the lexicographical order. And then I arrange, let's say this is ordering, Xi0, Xi1 up to Xi9. And I order the matrices accordingly. So this is Mi0, Mi1, Mi2, and up to Mi9. So Xi0 comes first in the lexicographical order, then Xi1. Now for all of this, I know that Xaij, Mij, Bij is in V bar. I apply a similar claim that I did before. So if this was not the lexicographical minimal word, then I could have easily replaced one of this. Let's say I could have replaced this Mi7 with a smaller matrix Mi2, right? So which is not the case, because I assume that the word I have initially is the minimal one. So this replacement is not possible, and hence I actually have a huge word which repeats in my word. So let's say my Z is of the form U1x W1. I can also write it as U2x W2. So there is this huge chunk which repeats, huge factor which repeats in the word. So now, how do you get the special form? It's a bit, yeah. So you can see how you get the special form. So you can see that this portion, these two words are the same. So basically, this V and V, let's say this is the word V. You have the same V here, right? Now this V is a prefix of X there. So naturally, V will be a prefix of X here as well. Now again, you can match these two portions. The upper portion will be a V. Now VV is a prefix of X. PV will be a prefix of here as X here as well. So this process can go on, right? So you do this, and ultimately you will have a prefix of V, which is V dash here, and then you can map it here. Like you can even argue that this is V dash, but we don't really care about it. So now you can show that this the length of V1, V, and W1 are all polynomially bounded. It's not hard to show that. So again, if you have multiple cuts, you can show that this portion has the form U y1 raised to R1 W1. And this is, let's say, some W2, because the counter value is polynomially bounded anyway. And the remaining portion, you can show it as some U2 y2 raised to R2 W2, or W. So you have the special word lemma here. Now, with this special word, you can easily show that the equivalence of this ODCA, weighted ODCA, where weights come from a field, is actually desirable and can be done in polynomial time. So we have, So the idea is like you bound the maximum counter value encountered during the run of the minimal witness using these techniques. And then you can then construct a weighted automata up to that counter value and then check for equivalence. Now we have other results like regularity. Given a weighted ODCA, can you check whether it is equivalent to a weighted automaton? It can also be done in p time. And then the covering problem. So for regularity, again, 5 minutes, yeah, enough. So for regularity, you do a similar technique. Instead of, let's say, pumping down, you show that you can pump up some portion infinitely many times, and hence you can find some infinitely many equivalence classes of that. Yeah, so regularity is also in P, and we have a covering problem. Let's say, given two ODCAs without initial configuration, determining whether for all initial distributions of A1, does A2 have an initial distribution which makes them equivalent. So this problem is also in P. So these are the results that we have. Yeah, so we have shown that this Covey's reachability problem for ODCA is in P, and the equivalence and regularity for ODCA or for weighted ODCAs is also in P. So so these are the existing results for equivalence. We know that for DPD is desirable, for NPD is undesirable. For probabilistic automata, we know it to be P. For weighted ODCA, we have shown it to be P. But for deterministic stack push-on automata and probabilistic push-on automata, they are still open problem. So the next step would be to look at maybe say what happens if the stack operations are always deterministic. What can you tell about equivalence? So also you can maybe take a look at let's say non-real time versions of it, where you can have epsilon moves as well. So that's also a future direction.